A silence gathers over the solar wind, a silence not of sound but of anticipation. Beyond the reach of planets, in the still black corridors between stars, something moves with glacial certainty. It is not a new body in the cosmic sense. Its atoms were born before our sun itself, in the embers of older stars. Yet to us, it is new, unseen, unexpected, a shard of ice and dust, modest in size but infinite in meaning, drifts inward toward the realm of the Sunday. Astronomers, gazing into the sky with machines designed to catch faint wanderers, have noticed it, a messenger from another system. It comes not alone in legacy. Humanity has already met two such interstellar guests, Oumuamua in 2017, with its elongated, tumbling silence, and Borisov in 2019, a more traditional comet dressed in gas and dust. Both left us with more questions than answers. Now, in 2025, the third has arrived, 3I divided by Atlas. Its name carries both clinical designation and mythic weight. Atlas, the titan condemned to bear the heavens, now lending his name to an icy fragment that challenges us to bear the uncertainty of the cosmos itself. The opening images of this comet are faint, a dot gliding almost unnoticed among thousands of stars. Yet within that point lies a story of unimaginable distance. Its trajectory is hyperbolic, not bound to the sun, not born here, but slicing through with a momentum that no planetary gravity can hold. We know what that means. It is an interstellar traveler, untouched by the patterns that shaped our own solar system. It comes from another nursery of worlds, or perhaps from the dark void between them. The mystery deepens not in whether it will strike us. Calculations already place its closest approach well away from Earth, but in what it carries. Imagine the body approaching the sun, its frozen surface awakening as sunlight gnaws into ices untouched for billions of years. What gases will spill into space? What dust will be released, drifting into tails that stretch millions of kilometers? Each atom is a record of a star system we cannot see, a chemistry formed under suns that are strangers to us. And yet, behind the science, there is the shadow of unease. For every equation that reassures us of safety, imagination writes another scenario. What if its nucleus, fragile from eons of cosmic rays, fractures suddenly near Mars? What if clouds of debris, invisible and sharp, cross the paths of orbiters and probes? What if its chemistry hides compounds volatile in ways our models do not predict? Catastrophe may be unlikely, but in the stillness of the sky, worst-case possibilities accumulate like silent thunderclouds. Comets are time machines, fragments of the past locked in ice. But interstellar comets are more than that. They are time machines from another timeline. 3I divided by Atlas is not part of our history. It is an artifact from a different story, a piece of evidence from a system of which we may know nothing. And in that difference lies a challenge. Every prior law of cometary physics, every expectation shaped by centuries of watching Halley, Hale-Bopp, or Shoemaker-Levy, may stumble when applied to this stranger. The opening hook of its story is not brightness or spectacle. It is the quiet reminder that we are not alone in the material sense. Other systems shed fragments. Other suns lose their children to gravity's caprice. Those fragments drift, crossing gulfs that make light itself seem slow, until at last one slides into our gaze. If the universe is a vast ocean, then 3I divided by Atlas is driftwood washed ashore, bearing marks of a storm we never saw. There is something deeply human in the way we respond. Astronomers tighten their ephemerides, refining orbit predictions with each exposure. Engineers quietly review spacecraft safety margins. The public asks, could it strike us? And storytellers, ancient and modern alike, sense the myth. Atlas again, bearing the heavens, his weight unending. Now humanity bears the burden of interpreting a cosmic messenger whose meaning may remain elusive. The worst-case scenario may not be a literal impact. It may be subtler, more haunting. That this comet arrives, shows us glimpses of chemistry and dust, and then leaves without revealing its true origin. That it passes us by, withholding answers, reminding us that the universe still keeps most of its secrets. Yet here, in its first whispering approach, 3I divided by Atlas already achieves something profound. It forces us to look up, to wonder again, to realize that the galaxy is not still, that stars do not live in solitude, and neither do their fragments. We are embedded in a traffic of strangers, and each arrival is both gift and warning. So the story begins in silence, in awe, in unease. A shard of ice drifts inward, carrying with it the chemistry of another sun. We do not yet know if it will merely display or also disrupt. We do not yet know if it will answer our questions or deepen them. But we know this. In its faint light, we see reflected our own fragility, our curiosity, and our restless need to understand. In that awareness lies the true opening of this tale, the moment humanity realizes that the worst-case scenario is not always collision or destruction. Sometimes, the worst case is to be confronted with the infinite unknown and to know how little we truly understand. The night sky over Chile was clear, crisp, and deceptively quiet when a robotic telescope turned its gaze across the constellations. The Atlas Survey Asteroid Terrestrial Impact Last Alert System had been designed for vigilance, a sentinel watching for near-Earth objects that might arrive too late for comfort. On the 1st of July 2025, its cameras captured a faint speck moving against the fixed stars, almost unremarkable at first glance. A point of light, barely above the detection threshold, tracing an arc invisible to any unaided eye. Yet in that tiny displacement, in those fragile pixels, a story had begun. Atlas was not searching for the extraordinary that night. Its mission is mundane only in appearance, to find asteroids, comets, and fragments that might endanger Earth. Each night, it sweeps the sky, recording images, subtracting one frame from another to isolate the movers from the stillness of the heavens. This is how many comets have been found, how asteroids are catalogued, how orbits are refined. But this speck behaved differently. It moved faster than expected for an object so distant, its apparent motion not aligned with the orbits that belong to our sun's family. The computers flagged it, and human eyes confirmed it, a discovery worth reporting. The alert spread rapidly through astronomical channels. Within hours, other observatories were targeting the same coordinates. Confirmation is essential. A single sighting is nothing without independent verification. By the following night, the arc extended, the path grew clearer, and the whispers began. This might be interstellar. The phrase carries weight. It had been uttered only twice before in recorded science, and each time it had rewritten our understanding of what the cosmos delivers to our doorstep. The faint glow suggested activity sublimation of ices, perhaps carbon dioxide or carbon monoxide escaping into space. Already, it was different from Oumuamua, which had revealed no tail, no coma, no obvious chemistry. It seemed closer in spirit to Borisov, whose bright plume announced its cometary nature. Yet the context was everything. To find such a visitor was rare. To do so again within a single generation was astonishing. The cosmos was reminding us, the solar system is not a sealed vault, but a crossroads where strangers may pass. Discovery is never only about data, it is about the people behind the instruments. Astronomers at Atlas, trained to sift through the noise, felt the thrill that comes when a new object reveals itself. They knew the routine report to the Minor Planet Center, publish preliminary coordinates, await follow-ups from the global community. Yet, they also felt the weight of possibility. What if this was the next Oumuamua, the next unsolvable riddle? What if it carried chemistry unseen in any solar system comet? Other telescopes joined the chase. Pan, stars in Hawaii, ground-based arrays across Europe, the orbital gaze of Hubble. Each added precision, each tightened the curve of the orbit. And with every additional data point, the case strengthened. This body was not bound by the Sunday. Its eccentricity exceeded unity, a hyperbolic trajectory unmistakable. The whispers became conviction. The third interstellar visitor had been found. There is a moment in discovery where awe overtakes caution, when the implications bloom larger than the facts. For Atlas, that moment came swiftly. A survey telescope, designed to guard us against impact, had instead offered a reminder of our cosmic vulnerability in a different form. We are open to visits from beyond. Our solar system is porous. The barriers we imagine between stars are not barriers at all. They are distances, vast but not insurmountable for the debris flung from other systems. The earliest nights of observation are always filled with uncertainty. Was the brightness stable? Did it flare? Was the coma expanding in proportion to its distance from the Sun, or behaving oddly? These questions circulated among scientists, and in their cautious notes lay an undercurrent of excitement. For every detail pinned down, new anomalies appeared. Its orbit suggested it would pass within a range to Mars, not Earth-safe, but close enough to matter for machines circling that red world. Its activity suggested volatile ices buried within, preserved since the dawn of another planetary system. Discovery is never just a matter of sight, it is also a matter of meaning. When Oumuamua was spotted, the world wondered if it was artificial. When Borisov blazed across the sky, the wonder was how ordinary it looked, a comet like any other, and yet not ours. With 3I divided by Atlas, the mood shifted again. Its faint glow, its swift arc, its strangeness, all invited speculation. The first images looked unremarkable, yet the implications were vast. Thus began the unfolding of the narrative. On that July night, a speck was seen. By dawn, it was a suspect. By week's end, it was a herald. A new interstellar traveler had entered the annals of astronomy. The find was not merely another line in a catalogue, but an invitation to measure, to imagine, to confront once again the fragility of our place in a universe that is more open, more porous, more restless than we admit. In the taxonomy of the heavens, names matter. They are not mere labels but anchors of identity, a way for humanity to pin down what drifts beyond reach. When the faint speck confirmed itself as real, the Minor Planet Center assigned its first formal designation, C divided by 2025 N1, a provisional name describing its cometary nature, its year of discovery, and the half-month interval of its first detection. Yet this was only the beginning. Soon, a second title joined, 3I divided by Atlas. The 3I speaks with quiet weight. It marks this object as the third interstellar body formally recognized by science, following the enigmatic 1I, Oumuamua, and the cometary 2I divided by Borisov. That numeral 3 is both small and immense. Small because it underscores the rarity of such discoveries. Immense because 3 is enough to suggest pattern where before there was only accident. The cosmos has now delivered a trilogy of interstellar visitors to our doorstep. They are not myth, but a category. They form a sequence, however incomplete, that implies continuity. If 3, then surely more. The Atlas suffix preserves the legacy of the survey that caught it first. The telescope's patient sweep across the Chilean night is forever written into the comet's name. Names serve history as much as science. embedding memory into the act of classification. In this way, 3I divided by Atlas is not just a body of ice and dust, it is also a monument to vigilance, to the quiet diligence of instruments designed for watchfulness. Designation became confirmation. With the orbit refined, its hyperbolic trajectory undeniable, astronomers announced this was a visitor from beyond the Sunday. The numbers themselves told the story. Its eccentricity exceeded unity. No gravitational bond to the solar system could explain its path. The arc traced through space was not elliptical, not parabolic, but a clean curve that testified to an origin among the stars. Humanity, in naming, acknowledged its alienness, a comet that belongs to no sun we know. The announcement rippled through the global scientific community. Within hours, observatories adjusted schedules, telescopes pivoted, instruments recalibrated, to capture early spectra, to refine ephemerides, to record brightness over time. Each measurement became a piece of evidence, and in each measurement was encoded the thrill of participation in something larger than routine science. This was not simply another comet. It was a shard of another system's history, a clue to the processes that unfold unseen in distant nurseries of stars. Comparisons were inevitable. Oumuamua had confounded with its strange shape, its lack of coma, its subtle accelerations. Borisov had reassured with its familiarity, behaving much like a solar system comet. 3I, divided by Atlas, immediately occupied a space between them, active like Borisov, yet distant and faint enough to conceal more than it revealed. Already, its uniqueness was apparent. To have 3 exemplars is to invite contrast, to sketch categories. It suggested that interstellar comets might be as diverse as stars themselves. Yet, beyond the technical, there was the symbolic. To call this object 3I divided by Atlas is to acknowledge a threshold crossed. No longer a one-time anomaly, no longer a mere curiosity. Interstellar visitors are now part of the scientific fabric. They are rare, yes, but not unthinkable. They are woven into the probabilistic tapestry of astronomy, expected though unpredictable, inevitable though unforecastable. They remind us that the solar system does not stand apart from the galaxy, but participates in its restless exchange of matter. For the public, the name itself became an incantation. Headlines spoke of 3I divided by Atlas, the third interstellar comet, and curiosity flared. To those less steeped in technicalities, it was simply a comet from another star. That phrasing carries mythic undertones. In ancient times, comets were omens, fiery messengers crossing the heavens with secrets. Now, with instruments sharper and knowledge deeper, the omen becomes evidence, but the aura of mystery remains. In scientific circles, the designation set the stage for all that followed. Every report, every dataset, every simulation would henceforth be filed under this name. In the archives of astronomy, 3I divided by Atlas would stand alongside Oumuamua and Borisov, forming a trilogy of cosmic outsiders. In the collective imagination, it would stand as both an individual and a type, one instance, yet also a symbol of all the wanderers yet unseen, waiting in the dark to cross our path. The act of naming, then, was more than ceremony. It was the first step in making the incomprehensible comprehensible. To name is to domesticate, to draw into language what remains beyond reach. And yet, even named 3I divided by Atlas retained its strangeness. Behind the clean numerals and tidy acronyms lurked the unanswerable. From what star was it torn? How long had it drifted? What collisions, what disruptions, what forces had cast it into the great gulf? No name, however precise, could close that gap. Thus, the christening of 3I divided by Atlas was both an ending and a beginning. An ending because it confirmed discovery, secured identity, and filed the comet within human knowledge. A beginning, because every question that matters, its chemistry, its structure, its risk, its meaning, remained open, waiting to unfold as the stranger drew closer to the Sunday. When the first orbital solutions emerged from the computers, they carried with them both reassurance and unease. Reassurance, because the numbers showed that Earth was safe. The new object, 3I divided by Atlas, would never come within threatening range of our planet. Unease, because its trajectory brushed uncomfortably close to the lanes of other worlds, and because its very path defied the familiar choreography of the solar system. Astronomers traced its arc backward and forward through time. The object was inbound from the outer dark, a line cutting across the sun's gravitational well, with no loop of return. The eccentricity was greater than the mathematical hallmark of a hyperbolic traveler. From the data, they reconstructed its passage. Perihelion would fall just inside the orbit of Mars, the point of closest approach to the Sunday. For Earth, the separation at its nearest would be about 1.8 astronomical units, a safe distance, nearly twice the span between Earth and the Sunday. But safe is a relative term. In celestial mechanics, even distant crossings concede uncertainty. The orbit, plotted against familiar ellipses, looked like a sword thrusting through a wheel. All planets move in near circles, bound by the sun's patient gravity. Comets native to this system trace long ellipses, looping out and then falling back in. But 3I divided by Atlas ignored these patterns. Its course was foreign, its energy unbound. That strangeness was itself part of the danger. Predictions for normal comets can be tested against centuries of precedent. Predictions for interstellar comets rest on 3 data points in all of human history. Even as astronomers breathed relief at Earth's exclusion, their eyes turned to Mars. For here was a coincidence of geometry. In early October 2025, Mars and the comet's path would align in the same sector of space. Not an impact, the separation remained wide, but a close passage that placed orbiters, satellites, and perhaps even surface rovers within the sphere of potential dust and gas. To scientists, it was an opportunity. Mars might serve as a forward outpost, a place to observe the comet up close. To engineers, it was a variable: dust flux, trajectory uncertainties, the possibility of fragmenting outbursts. The deeper strangeness lay in the comet's orientation. Its inbound trajectory suggested that it originated not from the familiar Oort cloud, nor from the flattened plane of solar system debris, but from a direction out of galactic context. It was tilted, skewed, cutting across our system like a messenger from a distant spiral arm. That tilt meant the solar wind would interact differently with its coma, shaping tails that might sweep through unanticipated volumes of space. Models diverged on how those tails would evolve and whether any planetary orbits would intersect them. This is where the tension sharpened. Impact was impossible, yet influence was probable. Dust grains invisible to the eye but dangerous to sensitive optics could be cast outward for millions of kilometers. Spacecraft en route to Mars, or already circling it, might have to navigate uncertainties measured not in kilometers but in particles per cubic meter. The geometry of its orbit gave no cause for panic, but every cause for vigilance. And so, from the very first orbital refinements, the narrative bifurcated. One voice said, "There is no danger. Earth is safe. This is a scientific gift." Another voice said, "We do not yet know enough. What if the nucleus shatters? What if outgassing alters the path of dust streams? What if the models fail?" Both voices were true, and in their tension the mystery deepened. In the long tradition of astronomy, orbital solutions are the closest thing to prophecy. They are calculations, not visions, but they carry the same weight, a glimpse of what will be. For 3I divided by Atlas, The prophecy was double-edged. Safe, yes, but also alien. Predictable in broad strokes, unpredictable in detail. The numbers banished apocalypse while leaving intact the subtler specters of disruption and surprise. Thus, by mid-July 2025, the orbital story of 3I divided by Atlas had crystallized. A hyperbolic visitor, perihelion inside Mars, Earth untouched, yet the system unsettled by its alien glide. A stranger that passed us by, yes, but close enough to stir questions about what it carried and what might yet unfold. As the object drew closer and instruments gathered more light, astronomers began dissecting the faint spectrum hidden within the glow. The colors of that light carried whispers of chemistry, fingerprints etched into photons. At first, the signatures seemed routine faint emissions of familiar gases, but then came the surprise. Ratios between carbon dioxide and water, between carbon monoxide and dust, hinted at a balance unlike any seen in most solar system comets. The coma was enriched in CO2 relative to H2O, a strange inversion of expectation. On Earth, carbon dioxide is a gas of climate and breath. In comets, it is a volatile that sublimates easily, vanishing into space as sunlight warms the nucleus. Normally, water dominates once comets cross into the inner solar system, with carbon dioxide as a trace companion. But here, the story seemed reversed. The gas cloud surrounding 3I divided by Atlas spoke of reservoirs frozen in conditions colder, darker, and perhaps older than those that birthed the comets we know. This imbalance forced new speculation. If the comet's ices were laid down in a nursery star system colder than ours, then carbon dioxide could have been trapped in larger quantities, sealed beneath crusts of dust. Or perhaps its parent star's radiation sculpted a chemistry alien to our expectations, leaving CO2 in abundance where water was scarce. Either way, the readings suggested that 3I, divided by Atlas, carried within it a chemistry unshaped by the sun, untested against the familiar arcs of solar system evolution. The implications reached further than numbers. Each molecule of carbon dioxide released into the coma was a relic of conditions billions of years past. They were fossils in gaseous form, carrying the memory of temperatures and pressures from a world no longer accessible. To detect them was to peer backward into a system not our own. For planetary scientists, it was exhilarating, a glimpse of comparative chemistry across interstellar gulfs. But it was also disquieting. Chemistry defines behavior. If the composition was skewed so heavily towards CO2, then the comet might outgas differently, with jets of carbon dioxide, driving forces stronger or less predictable than water sublimation alone. Non-gravitational accelerations, subtle but real, could push the nucleus off its expected path. Even small deviations, amplified over weeks, could alter where tails extended, what regions of space filled with dust, and what spacecraft might face. The discovery echoed through scientific meetings and urgent notes shared between observatories. Models of dust release had to be rewritten, predictions of coma density shifted. Conversations turned from curiosity to caution. If the comet were chemically exotic, then the assumptions underlying safe distances might be less stable than thought. The media, too, seized on the chemistry. Headlines spoke of alien ices, of comet with strange composition. For the public, it became another layer of mystery, another reminder that visitors from beyond the sun are not simply duplicates of what we know. They come with their own rules, their own dangers, their own riddles. And behind every discussion lay the whisper of the worst case. If 3I divided by Atlas harbored volatile rich layers beneath a fragile crust, then sudden exposure to sunlight could trigger violent outbursts. Jets could surge unexpectedly, shedding fragments, multiplying dust production, No danger to Earth, but perhaps danger to spacecraft, to delicate sensors, to fragile electronics traversing the thin atmospheres of Mars. Thus, chemistry, normally the quiet province of spectroscopy and lab analysis, became a character in the unfolding drama. The skewed balance of gases turned the comet into a puzzle that no orbital calculation alone could solve. It was not just a body moving along a predictable arc, it was an engine of volatile release, a system whose behavior could turn on hidden layers and unseen fractures. So the mystery deepened, not with a roar but with the faint lines of a spectrum. In those lines, astronomers read a tale of origins in the frozen dark, of chemistry out of balance, of potential instability cloaked in silence. And as the object crept closer to Mars's orbital lane, the question sharpened: what does this imbalance mean for what lies ahead? The Hubble Space Telescope, aging but still sharp-eyed, turned its glass toward the faint wanderer. Though designed for distant galaxies and cosmic expansion, its steady gaze proved equally valuable for measuring the intimate details of a comet's glow. Against the starfield, Hubble resolved not fine structure, but something more essential: limits. It could not paint the nucleus in detail, yet it set constraints on how large, how reflective, how active the body might be. The images came back soft, as expected. No telescope, even Hubble, could cleanly separate the nucleus from the surrounding coma at such distance. But analysis of brightness, coupled with assumptions about albedo, the reflectivity of cometary surfaces, yielded estimates. The nucleus could be no larger than a kilometer across, perhaps smaller, hidden inside its shroud of gas and dust. That upper bound carried significance. A smaller nucleus meant less total mass, less gravitational cohesion, more susceptibility to fracture. It also meant that the level of activity observed, faint though it was, might represent an unusually vigorous outgassing for its size. Astronomers compared the findings with earlier interstellar visitors. Oumuamua's nucleus had been inferred rather than seen, its dimensions controversial but certainly elongated, its surface bare and strange. Borisov's nucleus had been larger, a more ordinary comet by solar system standards. 3I divided by Atlas, with its modest size, fell between categories: big enough to sustain activity, small enough to raise questions about fragility. Limits can be more provocative than measurements. A ceiling of 1 kilometer is not just a number, it is a boundary within which uncertainty thrives. If the nucleus were half that size, then every gram of dust it shed was proportionally more dramatic, every jet more forceful relative to its mass. If closer to the upper bound, then it might endure its solar passage more steadily, releasing material with restrained dignity. Which was true, the data could not yet say. But even in ambiguity, there was revelation. Hubble's observations confirmed that this was not a giant. It was not a 10-kilometer behemoth like Hale-Bopp, nor a mountain-sized relic like Halley's nucleus. This was a smaller shard, a splinter rather than a boulder, a fragment that might once have been part of something larger. That alone altered risk assessments. Smaller bodies can be more volatile, more prone to sudden breaks. And in an interstellar context, they are also more likely to survive ejection fragments, light enough to be flung outward when stars interact, when planets migrate, when systems collide. The results were published, quietly at first, then amplified through scientific circles. Nucleus size is less than or equal to 1 kilometer became a defining phrase, repeated in papers, presentations, and press articles. The finding did not calm the imagination, it sharpened it. For a small nucleus meant less predictable stability. It could fracture under thermal stress, or spin faster as jets exerted torque, or disintegrate into multiple pieces. Such events, though not catastrophic on planetary scales, could transform the environment around Mars and around any spacecraft near it. And yet, Hubble also offered reassurance. The coma appeared symmetrical, unbroken, not the ragged debris of a body already failing. Brightness evolved smoothly, without the jagged spikes of an outburst. At least for now, the comet was intact, coherent, consistent. This was no Shoemaker-Levy in slow motion, no visible prelude to destruction. It was, as far as could be told, a disciplined traveler, shedding ices in measured silence. Still, scientists knew that discipline could be deceptive. Small nuclei can fail suddenly, outbursts can emerge without preamble. And so, while the size constraint gave confidence, it also compelled humility. The worst-case scenario was not erased. It was reframed. Not a giant's collision, but a fragment's fragility. Not extinction, but disruption. A risk to spacecraft, to instruments, to the fragile web of machines humanity has cast into the sky of Mars. Thus, Hubble's blurred images became part of the unfolding narrative. They told us less of what the comet was than of what it was not. They ruled out the giant, leaving us with the vulnerable. They denied us detail, but gave us a frame. And, within that frame, speculation flourished, carrying the story forward. An interstellar stranger, modest in size, still cloaked in mystery, but ever more tightly bound to human imagination. To understand 3I divided by Atlas, astronomers instinctively reached backward, comparing it to the two earlier visitors that had already etched themselves into the annals of science. The act of contextualization was inevitable. Oumuamua in 2017, Borisov in 2019, each a riddle, each rewriting the boundaries of what the solar system could expect from the galaxy. Together they formed the brief but growing lineage into which 3I now fit. Oumuamua was the first, and perhaps the most unsettling. It arrived silently, discovered too late to study in detail, already speeding away from the sun when telescopes turned toward it. Its light curve revealed a bizarre shape, elongated, tumbling chaotically. Its lack of coma, its apparent dryness, and its subtle non-gravitational acceleration left questions unanswered. Was it rock, ice, or something stranger? Speculation raced far ahead of data. Some wondered whether it was artificial, a fragment of alien technology. Others proposed it was a shard of an interstellar planetesimal, baked dry by eons of exposure. What mattered most was that Oumuamua defied categories. It looked like nothing we had seen before. Then came Borisov, a comet that reassured even as it startled. Unlike Oumuamua, Borisov bore the hallmarks of a more familiar cometary body, a nucleus wrapped in a bright coma, a sweeping tail trailing across the stars. Spectroscopy revealed cyanide, water, and other common cometary molecules. Its behavior matched what was known from solar system comets, as if to remind us that interstellar wanderers can also be ordinary, their strangeness lying only in their origin. Borisov was alien, yes, but familiar in its display, a comet by every standard definition. Now, 3I divided by Atlas entered the stage. Where did it fall between these extremes? Already it showed activity, a glow of escaping gases. It was no silent, barren rock like Oumuamua, but it was also not the dramatic beacon that Borisov had been. It was dimmer, more reticent, revealing itself cautiously. Its chemical ratios, skewed toward carbon dioxide, suggested divergence from solar system norms, a sign of origins under conditions unlike our sun's nursery. And its size, modest and constrained, positioned it as more fragile than Borisov, more vulnerable to disruption. In the triangle of comparison, a pattern emerged. Oumuamua had challenged our imagination by being too strange. Borisov had comforted us by being almost ordinary. 3I, divided by Atlas, balanced uneasily between them, alien enough to unsettle, commentary enough to reassure. It was both familiar and foreign, a bridge that showed interstellar objects were not anomalies, but a spectrum. Together, the three suggested that the galaxy is littered with shards of planetary birth, each carrying a different story of chemistry and structure. The scientific impact was profound. With a third data point, interstellar comets could be discussed as a class, however embryonic. Their diversity now resembled the diversity of the solar system's own comets, where some are rich in carbon monoxide, some fractured easily, some remained quiet until close to the sunday. By extension, the diversity of planetary systems beyond ours became tangible. If their debris could reach us, then their variety was not theoretical but visible, measurable, undeniable. Yet the comparisons also sharpened the anxiety of the worst case. Oumuamua had shown that an interstellar visitor could appear without warning and escape before we understood it. Borisov had shown that they could be active and dusty, capable of seeding space with material. 3I divided by Atlas combined these lessons. An active, dusty comet, fragile in size, unpredictable in behavior, passing close enough to Mars to be a factor in operational planning. Each precedent fed into its shadow. Astronomers, philosophers, and poets alike felt the resonance. Here was a trilogy of messengers, 3 emissaries in less than a decade, after millennia in which humanity had never recognized such a thing. Was it coincidence, or a sign that our instruments had only now become sharp enough to notice the traffic? Was the galaxy suddenly more generous with fragments, or had such wanderers always passed unnoticed? The question itself carried weight. It reminded us of our blindness, of how much sky had gone unseen before technology widened our gaze. Thus, 3I divided by Atlas did not stand alone. It stood as part of a growing chorus, a sequence that spoke not just of isolated anomalies, but of a galactic environment more alive with motion than we had assumed. And in that chorus, its voice was distinct, carrying new harmonics of chemistry, fragility, and potential hazard. It was not the strangest, nor the most familiar, but perhaps the most consequential, arriving at a time when humanity's machines orbit other worlds and when even a modest dust storm in space could ripple through fragile electronics. Comparison, then, was not merely intellectual, it was preparation. By studying what Oumuamua had withheld, what Borisov had revealed, and what 3I divided by Atlas now suggested, we learned not only about them but about ourselves, about the limits of our knowledge, the risks we face, and the humility required when confronted with the galaxy's wandering debris. As weeks of observation accumulated, astronomers began to notice that the comet's path was not perfectly smooth. The mathematics of gravity predicted a clean hyperbolic arc, a trajectory written by the sun's pull and the initial velocity with which 3I divided by Atlas had entered the solar system. Yet the data whispered otherwise. Residuals in the orbit fit hinted at tiny, persistent deviations. Something more than gravity was at work. These subtle shifts are the fingerprints of outgassing. As sunlight penetrates the comet's crust, frozen volatiles sublimate into jets. Each jet is a miniature thruster, releasing gas and dust into the void. To the naked eye, they are streams of beauty. To equations, they are accelerations. Over days and weeks, the accumulated effect nudges the comet from its gravitational path, an invisible hand pushing on the nucleus. For ordinary comets, these forces are well known. For an interstellar visitor, whose chemistry may differ and whose crust may fracture in alien ways, they are far less predictable. The numbers were small changes measured in fractions of kilometers per day, yet in celestial mechanics, small is enormous. A trajectory altered by a few arcseconds today can translate into thousands of kilometers difference weeks later. If Earth is not threatened, the question remains, where will the dust tails sweep? What orbital corridors might intersect the haze? For Mars, with its satellites and probes, such uncertainty could be the difference between serene observation and hazardous encounter. Scientists fed the data into models, adjusting parameters for sublimation rates, rotational spin, jet geometry. But uncertainties multiplied. The nucleus size, still only bounded by Hubble's limits, meant that even modest jets could have disproportionate influence. The carbon dioxide, rich chemistry implied stronger, more impulsive outgassing than water alone, and if fractures developed, exposing new ices, accelerations could spike unpredictably. Here lies the seed of a worst-case scenario. Not a collision, but a cascade of unpredictable non-gravitational forces steering dust streams across paths we thought were clear. Even a slight change in jet direction could shift a tail by millions of kilometers, placing spacecraft in environments far denser with particles than expected. And spacecraft are fragile. Their sensors, optics, and solar panels are not built for sandblasts of interstellar debris. History offered sobering reminders. Shoemaker Levy 9, torn into fragments by Jupiter's gravity, had shown how comets could surprise. Even small, faint bodies had produced bright flares and violent disintegrations when heated. 3I divided by Atlas carried no risk of slamming into a planet, but it carried the potential to confound models, to alter its behavior in ways beyond calculation. And each uncertainty widened the margin of what worst case might mean. Astronomers knew that refinement would come with time. Each night of tracking shrank the error bars, tightened the ephemerides, clarified the non-gravitational parameters, yet time was also a constraint. The closer the comet approached perihelion, the more volatile its behavior would become. The race was between observation and transformation. To understand it before it changed, or to adapt as it did. Public reports framed the story with balance. The comet posed no danger to Earth, they emphasized. But among scientists, the conversation was more nuanced. Safe meant only one kind of safety. It did not erase the possibility of disruption to orbiters, of unexpected meteoroid showers, of dust densities higher than instruments could endure. For engineers responsible for Mars missions, those subtle accelerations were not academic. They were warning signs, early indicators of a system in motion that might yet surprise. In those deviations, in the barely perceptible drift from gravity's perfect script, the comet revealed both its fragility and its power. Fragility, because outgassing meant it was shedding itself into space, eroding under the sun's glare. Power, because each invisible puff of gas was enough to shift an interstellar traveler across millions of kilometers of empty sky. Thus, the narrative of 3I divided by Atlas grew deeper. No longer was it only a body on a hyperbolic path. It was also a living engine, its course written not just by the pull of stars, but by the breaths of its own volatile heart. And in those breaths, the seeds of risk, mystery, and revelation continued to grow. Dust, the smallest ingredient of a comet, yet often the most consequential. Around 3I divided by Atlas, dust emerged as both signature and threat. To the naked eye, it is what turns a comet into a spectacle, the shimmering tail, the soft halo of the coma. But to scientists and engineers, it is infrastructure in miniature, tiny grains that shape light, alter orbits, and potentially menace the machines we have scattered through space. The release of dust begins with sublimation. As volatile ices heat, they drag particles with them, lifting grains from the surface into surrounding space. For solar system comets, these grains span a spectrum, submicron specks that scatter sunlight into haze, larger sand, like particles that drift sluggishly, even pebble-sized fragments that can strike spacecraft with surprising force. For 3I divided by Atlas, the chemistry hinted at stronger carbon dioxide-driven jets, capable of lofting larger grains with greater velocity. This meant its dust environment could differ sharply from the comets humanity has catalogued for centuries. Dust density is more than a poetic veil, it is a measurable hazard. Even at a few particles per cubic meter, relative velocities in space transform dust into bullets. A grain no larger than a salt crystal, striking a spacecraft at tens of kilometers per second, carries kinetic energy sufficient to pit metal, scar optics, or damage solar arrays. Protective shielding exists, but no spacecraft is armored against prolonged passage through dense plumes. And unlike meteor showers on Earth, there is no atmosphere on Mars or in deep space to burn the particles away. Astronomers began constructing models of potential dust output. They accounted for nucleus size, activity rates, tail geometry, and the comet's proximity to Mars's orbit. The results were soberingly ambiguous. Some models predicted that Mars and its satellites would pass well clear of any dense tails. Others suggested a possibility low, but not negligible, that orbiters could cross through diffuse streams. The uncertainty was magnified by the non-gravitational accelerations already detected. If the jets shifted the comet's orientation, tails might sweep across broader arcs than expected. Dust also has subtler effects. It scatters sunlight, creating halos that can confuse instruments designed to lock onto stars. It charges electrically, interacting with solar wind to produce plasma tails of unpredictable behavior. For spacecraft relying on precise orientation, even momentary interference could trigger safe mode shutdowns. For landers on Mars, the chance of visible meteor activity was both opportunity and risk. A chance to study interstellar particles in situ, but also a possibility of sensor overload or micrometeoroid strikes on delicate instruments. The worst-case scenarios multiplied quietly in technical papers. A fragmenting nucleus could shed far more dust than anticipated, creating clouds of particles kilometers across. A sudden outburst could saturate a corridor of space with densities far above the norm, overwhelming shielding assumptions. Even if Earth remained untouched, the network of orbiters circling Mars, each a billion-dollar investment in exploration, could face exposure to hazards beyond their design margins. And yet, dust is also knowledge. Each grain carries isotopic ratios, mineral structures, histories of condensation around distant stars. In its tiniest components, dust preserves the birth cry of another solar system. For scientists, to collect such grains, even indirectly through spectral analysis, was to hold pieces of an alien nursery in hand. The risk and the reward were inseparable. Thus, dust became the quiet antagonist in the unfolding story of 3I divided by Atlas. Invisible to the casual observer, it loomed large in calculations and caution. It reminded humanity that the universe's smallest fragments can wield the greatest influence, that cosmic beauty often hides microscopic danger. For in the luminous tale stretching behind this interstellar wanderer, the poetry of starlight and the physics of survival were inseparably entwined. As the comet drifted inward, sunlight grew harsher upon its nucleus. What had been inert for millions of years in the interstellar dark now faced thermal stress it had never known. Ice expands as it warms, dust contracts and shifts, cracks deepen. For a small body like 3I divided by Atlas, such stresses can be decisive. Its surface, once armored by eons of cosmic radiation, now became vulnerable to fracture, and fracture is the first step toward chaos. Astronomers modeled how heat would penetrate its crust. The upper layers, darkened by space weathering, absorbed sunlight efficiently. Beneath lay ices of water, carbon dioxide, carbon monoxide, each with a different volatility, each awakening at a different threshold. Where layers met, stress concentrated. A fissure could widen into a vent into a canyon. Entire slabs might shift, exposing fresh ice to the glare of the Sunday. When this happens, outgassing multiplies and jets erupt with greater force. Historical precedent was sobering. Comet 17P, divided by Holmes, had exploded into sudden brilliance in 2007, brightening a millionfold in a single night as its nucleus fractured internally. Comet Ison, hailed as a comet of the century, disintegrated near perihelion in 2013, undone by thermal stress it could not withstand. Shoemaker-Levy 9 had been torn to fragments by Jupiter's tidal forces before crashing spectacularly into its atmosphere. In each case, the trigger was different, but the result the same: instability, multiplication of surface area, and unpredictable debris release. For 3I divided by Atlas, the risk was magnified by its small size. A nucleus no larger than a kilometer could not absorb much strain. If fissures propagated, the body might fragment wholesale, becoming a cluster of smaller pieces, each shedding dust and gas on its own. Such a transformation would rewrite predictions overnight. Instead of a single predictable coma, orbiters near Mars might face a swarm of faint fragments, a lattice of dust corridors impossible to model in advance. Scientists weighed probabilities cautiously. Not every small comet disintegrates, many endure. But the chemistry of 3I divided by Atlas, its apparent richness in CO2, suggested higher volatility. Carbon dioxide sublimates at colder temperatures than water ice, producing outbursts at distances where most comets still slumber. If hidden reservoirs of CO2 lay beneath thin crust, their sudden exposure could act like a subterranean explosion. The release might fracture the body further, triggering a chain of instability. Thermal stress also influences spin. Outgassing jets act as thrusters, altering rotational speed. If the comet's spin rate accelerates, centrifugal force can surpass structural strength. Bodies already weakened by fissures may shed large chunks. A boulder sliding from a cliff face, a wall collapsing into vacuum. Each event adds momentum, scattering fragments into unpredictable paths. For spacecraft, the difference between a dust-rich coma and a debris-laden swarm is the difference between manageable hazard and mission-threatening crisis. The worst-case visions were stark. A sudden breakup near Mars's orbit could seed the surrounding space with clouds of particles. Even if they posed no direct danger to Earth, they could alter conditions for orbiters and rovers, forcing mission controllers to consider contingency safe modes. Instruments not designed for such environments could be overwhelmed. Panels could be scarred, optics fouled. The cost would not be measured in lives, but in knowledge, in silences where data should have flowed. Yet, within the danger lay promise. A breakup would expose interior layers of a truly alien body. Spectra might reveal chemistry unseen in solar system comets, isotopes that speak of other stars' histories. Fragments could serve as natural experiments, showing how interstellar matter behaves under solar radiation. For scientists, catastrophe could be opportunity. For engineers, it would be trial by fire. Thus, the comet, in its silent glide, embodied a paradox. It was fragile, vulnerable to sunlight, and yet dangerous precisely because of that fragility. The very cracks that might destroy it could also multiply its influence, turning a modest wanderer into a sprawling, unpredictable system. And so, as telescopes recorded its every shimmer, the question lingered: would 3I divided by Atlas endure its passage, or would it unravel before our eyes? In that uncertainty lay the tension of the story, the thin line between cosmic spectacle and worst-case scenario. Attention turned toward Mars. Orbital mechanics placed the red planet near the line of passage, its orbit skimming close to the geometry of the comet's trajectory. No one feared an impact. Calculations ruled that out with certainty, but proximity alone carried significance. For spacecraft circling Mars, the encounter could become more than observation, it could be exposure. By early models, the comet would pass perihelion in mid-October 2025, just inside the orbit of Mars. At closest approach, the separation between Mars and 3I divided by Atlas might shrink to a few tens of millions of kilometers, a cosmic breath by planetary standards. In celestial terms, that was far. Yet for spacecraft, which operate without the shielding of atmospheres, the concern was not distance, but environment. The orientation of the comet's coma and tails, the direction in which dust and plasma would be carried by the solar wind. The possibility emerged that Mars itself could cross through diffuse portions of the tail. Even if only the outermost streamers, the encounter would be unprecedented. A planet brushed by the dust of an interstellar comet. For orbiters, Mars Reconnaissance Orbiter, Massachusetts VEN, the European Trace Gas Orbiter, India's Mangalan, and newer arrivals, the event represented both an opportunity and a challenge. Instruments designed for atmospheric science or surface imaging might suddenly find themselves tasting particles from another star system, but their circuitry, solar panels, and optics would also face risks, however minor, of abrasion, overload, or contamination. NASA and ESA engineers quietly ran simulations. Past experiences offered guidance. In 2014, comet Siding Spring had passed within 140,000 kilometers of Mars. An extraordinarily close shave. Space agencies responded by temporarily repositioning orbiters to the far side of the planet during the densest period of dust passage. The result had been successful. The spacecraft survived unscathed, and Mars itself briefly acquired a cometary halo. That event became the template for preparation now. But 3I, divided by Atlas, was not Siding Spring. Its interstellar origin meant its chemistry, activity, and dust distribution could be unlike anything modeled from solar system precedents. Its carbon dioxide, rich jets might expel grains with higher velocities. Its modest size meant it could fragment suddenly, releasing dust clouds that models had not anticipated. The comparisons were useful but imperfect. Engineers were forced to hedge, preparing for uncertainties rather than repeating past playbooks wholesale. For scientists, the prospect was electrifying. Imagine an orbiter's spectrometer detecting isotopes that originated in a star system light years away. Imagine MAVEN, designed to study Mars's atmosphere, sampling atoms from an alien nursery. The data could rewrite theories of planetary formation, giving us direct contact with the building blocks of other worlds. To risk was also to learn. For mission planners, however, risk was the operative word. The worst-case scenarios, circulated in technical memos, included possible tail crossings that deposited dust densities an order of magnitude above safe levels. Even without catastrophic strikes, fine particles could degrade solar panels, scatter light into sensors, and accumulate on optical surfaces. Mars rovers were shielded by atmosphere, but orbiters were exposed. Protective maneuvers might mean suspending operations, entering safe mode, or reorienting spacecraft to minimize surface area facing the flow. The discussion thus became twofold: an unprecedented scientific opportunity and a potential hazard management exercise. Both narratives unfolded simultaneously. Astronomers issued ephemerides and brightness predictions. Engineers drafted contingency plans. The comet was no longer an abstraction moving through the outer sky. It was a visitor whose presence could touch our instruments, whose breath could graze another planet. the symbolism was powerful. For the first time in history, humanity had machines stationed around another world, and that world was about to receive a passing emissary from the stars. It was as if Mars had been chosen as the stage for an encounter Earth itself was spared. In the coming months, the red planet would stand in our stead, facing the plume of an interstellar comet. Whether danger or gift, the event would be recorded, measured, lived not in myth but in telemetry. Mars is not Earth. Its atmosphere is thin, barely 1%. The density of ours and its magnetic field is weak, broken into patches rather than a global shield. For ordinary space weather, this means Mars is vulnerable. The solar wind strips its upper atmosphere, radiation seeps to the surface, charged particles dance unhindered. For a passing comet, it means the red planet offers little resistance. Dust and plasma, carried by 3I divided by Atlas, could interact directly with the Martian environment, altering both sky and ground in ways unfamiliar to our models. The plasma tail of a comet is a conduit of charged particles, swept outward by the solar wind. On Earth, the magnetosphere deflects such streams, channeling them toward the poles, where auroras bloom. On Mars, the story is different. With no global field, cometary plasma would couple directly to the atmosphere, colliding with molecules of carbon dioxide and nitrogen. Briefly, Mars might glow with interstellar auroras, luminous curtains ignited not by our sun alone but by the chemistry of another system. Instruments aboard MAVEN, designed to study such processes, could detect the signatures, ultraviolet flashes, ionized species, an atmosphere temporarily rewritten by alien plasma. Dust grains, too, would play their role. Small particles, once ionized, can be steered by electromagnetic fields. Instead of drifting passively, they may spiral, accelerate, and collide with unexpected energy. Around Mars, where local magnetic anomalies dot the crust, dust could concentrate in arcs and eddies, creating localized storms invisible to the eye but potent to spacecraft sensors. For orbiters, even the smallest surge in particle density could confuse star trackers, trigger safe modes, or force controllers to shut down sensitive instruments. The surface of Mars, while shielded somewhat by atmosphere, might also bear witness. In 2014, when comet Siding Spring passed close, rovers recorded meteor activity in the thin sky. A similar event from 3I divided by Atlas was possible. Tiny flashes streaking across the Martian night, grains from another star system burning as meteors above alien sands. Such phenomena would not endanger rovers, but they would be profound. Mars, already a world of stories, briefly illuminated by the dust of a different sun. For planetary defense analysts, this was both opportunity and rehearsal. The thin Martian atmosphere meant orbiters were the true concern, but it also meant science could proceed unimpeded. Instruments sensitive to plasma, dust, and auroras could gather pristine data, unscreened by dense air or magnetic shielding. Every charged particle captured, every ultraviolet flash recorded, would be a gift of information. Yet behind every dataset lay the quiet caution. Could dust flux overwhelm electronics? Could plasma storms induce currents in solar arrays? The engineering solutions were practical. Spacecraft could be rotated to minimize exposed surface area. Instruments could be powered down during peak passage. Safe modes could be timed to coincide with predicted tail crossings. These measures had precedent. They had saved Mars orbiters during Siding Spring's encounter. Yet uncertainty remained. 3I divided by Atlas was no ordinary comet, and its chemistry suggested different dynamics. No one could guarantee that history would repeat cleanly. The philosophical resonance was striking. Earth had always borne the brunt of cosmic encounters in myth and memory, comets as omens, meteors as warnings. Now, in a twist of history, another planet stood in the line of passage. Humanity, through its machines, would experience it vicariously. We had extended ourselves into the solar system, and in doing so, extended our exposure to the galaxy's wanderers. The event underscored that planetary defense was no longer Earth-centric. Wherever our machines reside, the universe may follow. So Mars waited, a silent sentinel beneath a thin sky. Its crustal fields flickered weakly, its atmosphere lay exposed. Into this vulnerability, the plasma and dust of an interstellar stranger would soon flow. Whether as hazard or as gift, the encounter promised to leave an imprint on instruments, on data streams, on human imagination. For the first time, another world would stand as witness to an emissary from the stars. The geometry of encounter is everything. For 3 I divided by Atlas, the simple fact of alignment, sun, comet, planet, spacecraft, determined whether the event would be spectacle or risk. If the coma's faint gases trailed harmlessly into the void, Mars orbiters would see only a distant glow. But if the line of sight placed comet and sun in opposition, tales could extend across the very corridors where human machines travel, transforming instruments into accidental participants in the passage. Cometary tales are not monolithic. There is the dust tail, curved and graceful, following the nucleus along its orbit. There is the ion tail, straight and rigid, carried outward by the solar wind at high speed. Their directions differ, their densities vary, their extents stretch for millions of kilometers. In some orientations, both tails sweep away from planets. In others, geometry conspires to lay them directly across orbital paths. For Mars, the possibility loomed that even a shallow brush with a diffuse streamer could change routine into anomaly. Engineers remembered Comet Encke, whose dust trails Earth sometimes crosses, spawning meteor showers. They remembered Siding Spring, which brushed Mars with debris dense enough to warrant repositioning spacecraft. The lessons were clear. Geometry governs exposure, and exposure can be sudden. A few days' miscalculation, a minor shift in jet activity, and trajectories of spacecraft could intersect with regions they were never designed to endure. The risk was not of catastrophic impact grains, large enough to destroy spacecraft are vanishingly rare. The greater concern lay in cumulative exposure. Thousands of microscopic impacts can abrade solar panels, degrading their efficiency. Scattered dust can scatter sunlight, confusing star trackers and gyroscopes. Charged particles can induce currents that trigger false signals or force systems into safe mode. Each effect alone is survivable. Combined, they erode the reliability of missions built on fragile margins. Yet alongside hazard came opportunity. If Mars or its orbiters crossed even the edges of a tail, instruments could capture data no solar system mission had ever gathered. Direct sampling of interstellar dust. Mass spectrometers could taste the isotopes of alien grains. Cameras could record meteor streaks igniting in the Martian sky. Magnetometers could trace the charged particles' dance. Every risk carried within it the promise of discovery. Astronomers tracked the geometry relentlessly. Each new set of observations tightened predictions, shrinking the uncertainty. Still, non-gravitational accelerations, those subtle pushes from jets, left margins wider than comfort. A tail 1,000,000 kilometers wide could shift by millions more if outbursts altered the nucleus's rotation. Thus, the models carried caveats, probabilities, not certainties. Unlikely, but possible became the refrain. For mission planners, unlikely demanded preparation. Contingency timelines were drafted: when to pivot spacecraft, when to disable vulnerable instruments, when to rely on backup systems. In the best case, such measures would prove unnecessary. In the worst, they would prove insufficient. Either way, the alignment of Sun, Comet, and Mars meant the encounter was unavoidable. The geometry itself was the script, and the players, spacecraft and scientists alike had no choice but to follow it. Symbolically, the moment resonated. For centuries, comets were feared precisely because of their geometry, their sudden intrusion into familiar skies, their tails crossing constellations, their paths defying celestial order. Now, in an age of precision ephemerides, geometry still held power. It dictated not omens but outcomes, not prophecies but probabilities. And once again, humanity looked upward with a mix of fear and awe, awaiting what alignment would bring. Thus the anticipation sharpened. Would Mars cross the faint breath of an interstellar stranger, or would the tails sweep harmlessly past? Would orbiters become witnesses, or would they remain spectators? Geometry alone would decide a silent law of space, indifferent to our hopes, indifferent to our fears. Comets are notorious for their unpredictability, but few phenomena unsettle astronomers as much as the sudden flare of an outburst. One night, a comet is faint, subdued, a soft haze against the stars. The next, it brightens explosively, releasing torrents of dust and gas, its coma swelling into a sphere many times larger than before. Outbursts are both spectacle and warning, the sign that something deep within has shifted, ruptured, or awakened. For 3, I divided by Atlas, the prospect of such an event was more than academic. It was a variable written directly into the calculus of worst-case scenarios. Outbursts occur when buried reservoirs of volatile ice are exposed to sunlight, or when internal pressure overcomes the strength of the crust. They can be triggered by thermal cracking, by rotational stress, or by impacts from fragments too small to see. The result is sudden, brightness soaring, jets roaring, dust pouring outward at velocities that defy expectation. For a comet enriched in carbon dioxide, as 3I divided by Atlas appeared to be, the risks were magnified. CO2 sublimates more readily than water ice, releasing energy that can drive violent plumes, even at distances where most comets remain quiet. The historical record is dramatic. Comet 17P divided by Holmes erupted in 2007, brightening by a factor of 1,000,000, visible to the naked eye where once it had been obscure. The cause remains debated, perhaps a pocket of gas under pressure, perhaps a structural collapse, but the effect was undeniable, an entire coma expanding to engulf half the size of the Sun in the night sky. If 3I divided by Atlas were to experience anything similar, its dust environment would change instantly, flooding space with particles and gases. For Earth, such an outburst would remain a curiosity. The comet's orbit placed our planet far from harm, but for Mars and for spacecraft in its vicinity, the implications could be profound. A surge in dust output could thicken tails, extending them millions of kilometers beyond prior models. Orbiters that had expected to skim empty space might instead find themselves immersed in diffuse streams of alien grains. Instruments could be peppered, solar arrays sandblasted, sensors blinded by a haze no thicker than smoke but deadly in the vacuum of space. Engineers considered contingencies. Safe mode protocols could protect electronics. Rotating spacecraft to present minimal surface area might reduce damage. Yet none of these measures could fully negate the risks of a dense dust flux. The challenge lay in timing. Outbursts arrive unannounced, their onset faster than any warning system can provide. By the time brightness spikes are detected, the plume is already expanding outward at kilometers per second. For scientists, however, the temptation was irresistible. An outburst offers a glimpse into the interior, the layers of volatile ices and primordial dust hidden for eons. Spectrometers could capture gases freshly released, isotopic fingerprints unaltered by long exposure. Cameras could track particle dynamics, revealing how jets evolve in low gravity. A sudden eruption would be both hazard and opportunity, a natural experiment with data unlike anything else in astronomy. The philosophical undertone was striking. Outbursts embody the duality of comets themselves, fragility and ferocity bound together. A nucleus no larger than a mountain, no denser than packed snow, can hurl material into space with energies rivaling small volcanic eruptions. From weakness comes violence, from instability comes spectacle. For 3I divided by Atlas, this duality became a symbol of interstellar mystery. It was not only a messenger from another system, but a reminder that even the smallest wanderer can rewrite the script of expectation in an instant. Thus, the prospect of outburst hovered over every discussion. It was not inevitable, but it was possible, and possibility was enough. Models could not exclude it. Observers could not predict it. Mission planners could not ignore it. In the shadow of that uncertainty, the comet's quiet glow carried a hidden menace, the potential to become, overnight, something far brighter, far wilder, and far more dangerous than we had imagined. If an outburst is a flare of sudden energy, a breakup is something far more decisive, the unraveling of a comet's very structure. When a nucleus fragments, it ceases to be a single coherent traveler and becomes a swarm of smaller bodies, each following slightly different paths, each shedding dust in its own chaotic plume. For 3I divided by Atlas, with its modest size and fragile constitution, this scenario could not be dismissed. Indeed, some scientists whispered it was the most plausible outcome if stresses deepened on approach to the Sunday. The mechanics of breakup are complex, yet their essence is simple. A comet is a weak assemblage, a rubble pile, bound not by strength but by cohesion and frozen volatiles. Heat can open fissures, spin can strain connections, internal gas can pry slabs apart. When thresholds are crossed, the nucleus splits, sometimes into a handful of large fragments, other times into dozens of shards that crumble further into dust. Each fragment then becomes a comet in miniature, with its own jets, its own tail, its own unpredictable dynamics. In the history of cometary astronomy, breakups are not rare. Comet Shoemaker-Levy 9 shattered into a string of pearls under Jupiter's tidal grip, each bead later colliding with the giant's atmosphere. Comet Schwarzmann-Wachmann 3 fragmented repeatedly, leaving behind a debris field that still trails along its orbit. Even bright Hale-Bopp shed fragments, though it survived as a coherent whole. These precedents weigh heavily on models. Small comets are vulnerable, and interstellar ones, with unknown histories, may be more fragile still. For 3I divided by Atlas, the consequences of fragmentation would cascade. Instead of one predictable nucleus producing a stable coma, dozens of fragments would scatter, each releasing dust and gas. The result could be a debris cloud spanning tens of thousands of kilometers, complicating orbital predictions and hazard assessments. Mars orbiters, expecting a single stream, might face an intricate web of particle densities. Even diffuse clouds could raise the chance of impacts or sensor contamination. The worst-case images painted themselves starkly. A disintegration near Mars's orbit could saturate local space with meteoroids, from millimeter grains to larger chunks. For spacecraft, the risks would multiply. A single centimeter-sized fragment, though unlikely, could be catastrophic if encountered at tens of kilometers per second. Smaller grains, more common, could still pit surfaces, cloud optics, and erode solar arrays. For engineers, the challenge would not be survival of one great blow, but endurance under countless small strikes. Yet, as always, the hazard carried a mirror of discovery. A breakup would expose pristine interior ices to sunlight, releasing material that had been locked away since the birth of another star system. Spectroscopy could capture the freshest signatures, revealing isotopic ratios that whisper of alien formation conditions. Cameras could track fragments diverging, mapping the physics of disintegration in real time. For planetary scientists, a shattered comet is not a tragedy, but a laboratory, messy yet rich with insight. The philosophical layer deepened. A breakup embodies impermanence, a body that has wandered for millions of years, unbroken across light years, may unravel in the briefest span once it meets the Sunday. To watch such a fate is to confront cosmic fragility, the knowledge that endurance across eons can end in an instant. 3I, divided by Atlas, would thus become a parable, a voyager undone, not by collision or violence, but by the quiet inevitability of warmth and light. And still, the imagination lingered on darker contours. Could fragments cross paths with Mars itself, raining meteors into its thin sky? Could orbiters find themselves navigating an environment transformed overnight into a hazard field? Could rovers, cameras tilted upward, record streaks of alien meteors tracing the Martian night? These were possibilities, low in probability but profound in symbolism, for it would mean that another star's debris had touched not only our solar system, but the soil of another planet we explore. Thus, the prospect of breakup joined the list of looming uncertainties. Not certain, not even likely, but possible enough to shape both scientific plans and engineering precautions. A comet is both messenger and menace, and 3I divided by Atlas carried both roles in silence. Whether it endured or disintegrated, it forced us to reckon with instability as the essence of cometary life. And in that reckoning, humanity glimpsed again the thin line between knowledge and risk, awe and unease, opportunity and worst case. Rotation is destiny for a fragile comet. As 3I divided by Atlas advanced along its hyperbolic path, scientists speculated not only about its chemistry and orbit, but about its spin. For in a small body governed by jets, rotation can shift from gentle to catastrophic. Each plume of gas that escapes acts like a thruster, imparting torque. Over weeks and months, those torques accumulate, altering the rate at which the nucleus spins. And if the spin rate surpasses a critical threshold, centrifugal force can pry the body apart. This process, known as spin-up, has doomed many comets before. Observations of solar system fragments reveal telltale scars, surfaces split by torque, nuclei reshaped into binaries, clouds of fragments born of rotation gone unstable. For 3I divided by Atlas, the risk was heightened by its small size. A nucleus no larger than a kilometer has little structural strength. It is more snowball than stone, a fragile lattice of ice and dust. If jets exerted even modest but persistent torque, the body could spin itself to disintegration. Astronomers looked for signs. Photometric variations in brightness, rising and falling with rotation, might reveal its period. Subtle changes in coma asymmetry could hint at spin axes shifting, but the faintness of the object, combined with its distance, left measurements inconclusive. Uncertainty was itself unsettling. Was the comet tumbling chaotically, like Oumuamua had? Or was it rotating slowly, a sleeper soon to accelerate under the sun's warmth? The physics is unforgiving. Faster spin means lower stability. At some threshold, perhaps hours, perhaps minutes per rotation, the nucleus would shed surface layers, releasing slabs of ice and boulders into orbit around itself. These fragments, no longer bound, would drift outward, joining the dust cloud and complicating hazard models. A breakup triggered by spin would look sudden to distant observers, yet it would be the product of weeks of imperceptible acceleration. The consequences for Mars orbiters were clear. A nucleus shedding material under rotational stress could produce unexpected debris fields. Large fragments, though rare, would be the gravest threat, capable of catastrophic impact. Smaller chunks, more likely, could still overwhelm shielding, peppering spacecraft with high-velocity strikes. Unlike outbursts driven by volatiles, spin-induced fragmentation carries little warning. There is no spectral precursor, no brightening in advance, only the abrupt appearance of a swarm where once there was one. The paradox of spin lies in its subtlety. It is invisible in real time, hidden within the balance of jets and angles. Yet it governs fate as surely as gravity itself. In laboratories, models of torque and nucleus shape demonstrated just how fragile these bodies could be. A slight asymmetry in outgassing could double the spin rate in mere weeks. For an interstellar comet, whose internal layering might differ radically from our own, the thresholds might be lower still. For scientists, the idea was tantalizing. A spin-driven breakup would expose pristine interiors, releasing gas and dust from layers untouched by cosmic rays. Instruments might capture molecules otherwise impossible to detect. The physics of torque itself could be tested, offering clues to how small bodies evolve under sunlight across eons. But for mission engineers, fascination was tempered by caution. A body unraveling under spin could not be modeled easily, and its fragments might intersect orbital lanes unpredictably. The philosophical weight was unmistakable. Spin, in human culture, is motion, dance, continuity. For 3I divided by Atlas, spin was mortality, the silent turning that might undo it. A nucleus that had survived the emptiness between stars could, in its final weeks near a modest yellow sun, succumb to its own momentum. There was a poignancy in the image, a traveler undone not by violence from without, but by forces of its own making. Thus, as the comet inched closer, scientists watched for flickers of periodicity, for the quiet hints of torque at work. Would 3I divided by Atlas hold together, spinning gently past perihelion? Or would it, like so many fragile bodies before, spin itself into pieces, scattering its story across the void? The question, unanswered, became another thread in the tapestry of worst-case speculation, one more reminder of the delicate balance that governs wanderers of ice and dust. Beyond dust and ice, another force loomed. The sun itself, not as light, but as storm. The solar wind, a stream of charged particles flowing outward at hundreds of kilometers per second, meets every comet and reshapes it. For 3I divided by Atlas, the encounter was inevitable. Yet in 2025, the sun was not quiet. Solar maximum approached, a season of heightened activity. Coronal mass ejections, CMEs, erupted frequently, each a cloud of plasma capable of distorting tails, compressing comae, even sweeping dust away in violent bursts. The physics of interaction is intricate. A comet's coma is a cloud of neutral gas, but sunlight ionizes much of it, turning it into plasma. The solar wind then captures this plasma, dragging it outward to form the ion tail. When a CME arrives, the pressure rises sharply. Tails can be bent sideways, broken, or entirely detached. Astronomers have watched this happen before. A comet's elegant tail suddenly severed, floating free as the nucleus sprouts a new one. For 3I divided by Atlas, a visitor with alien chemistry, the effects could be even stranger. To spacecraft near Mars, such variability was double-edged. On one hand, a CME striking the comet could clear dust and plasma from certain regions, reducing hazard. On the other, it could redirect streams unpredictably, sweeping particles across orbits they would otherwise miss. A detached tail, caught in a solar gust, might intersect spacecraft by chance, a cosmic sandstorm driven not by the comet but by the sunday. The timing of solar weather became as important as the comet's own activity. Mars itself offered no global shield. Earth's magnetosphere often deflects or absorbs plasma surges, but Mars, with only local crustal fields, stood exposed. If a CME struck 3I divided by Atlas while its tails stretched near Mars's orbit, the interaction could pump charged particles directly into the Martian sky. Instruments like MAVEN's detectors might record auroras ignited not solely by the sun, but by the interplay of cometary plasma and solar fury. To see Mars lit by an interstellar aurora would be scientifically priceless, yet for orbiters, the charged environment could induce currents that disrupt operations. Engineers knew the hazards well. High-energy particles can damage electronics, corrupt memory, and degrade solar panels. Shielding mitigates but does not eliminate risk. Combined with dust exposure, plasma storms could multiply dangers. Dust grains, carrying electric charges, accelerated by fields, striking with more than kinetic force. The synergy of comet and solar storm created scenarios difficult to model, let alone defend against. Yet again, risk carried revelation. To watch how an interstellar comet responded to solar wind and CMEs would deepen understanding of plasma physics, of how stars sculpt the small bodies around them. The diversity of responses, tails bending, comae shrinking, particles dispersing, would teach us not only about the comet but about our own sun's influence across the heliosphere. 3I, divided by Atlas, in its vulnerability, became a probe, a natural experiment offered by the galaxy. The symbolism resonated. Here was a visitor from another star, meeting our sun not in tranquil light but in storm. It was as if the sun itself rose to greet the stranger, testing it with gusts and surges, bending its luminous tail like a banner in wind. And in that meeting we saw reflected our own fragility. Spacecraft trembling before plasma storms, instruments shielding themselves, while a comet endured forces both alien and universal. Thus, solar wind and CMEs joined the ledger of worst-case speculation. Not planetary collision, not extinction but disruption, interference, damage wrought by invisible storms amplified through cometary matter. The sun, our life-giver, became an accomplice in hazard, shaping not only the beauty of 3I divided by Atlas's passage, but the dangers it posed. And so humanity watched not just the comet, but the sun itself, knowing that in this cosmic encounter, the star's moods would be decisive. If solar storms could buffet the comet from without, tidal forces pressed upon it from within. Every comet that strays close to a massive body must contend with gradients of gravity, a subtle but relentless stretching. For 3I divided by Atlas, whose perihelion lay inside the orbit of Mars, the sun's pull would not tear it apart as Jupiter once did to Shoemaker Levy 9. Yet the influence of tides was not absent. Even gentle stresses can nudge fracture lines, coaxing fissures wider and altering the trajectories of dust grains as they lift free. Gravitational gradients act like invisible fingers. One side of the nucleus feels a slightly stronger pull than the other. For a solid mountain, such differences are negligible. But for a porous body of dust and ice, a rubble pile bound by cohesion more than strength, these differences matter. Each orbit is not an orbit at all for 3I divided by Atlas, but a single pass, yet even a single pass is enough to test its seams. As perihelion approached, the nucleus would feel its structure strained, not catastrophically, but subtly. It was in those subtleties that uncertainty thrived. The dust released under such stresses followed their own paths, not identical to the nucleus, but influenced by these gradients. A grain shed sunward might arc differently than one shed anti-sunward. The result, a coma and tails shaped not only by gas jets and solar wind, but by the invisible sculpting of tidal geometry. For astronomers modeling hazards, this added complexity. Predicting dust density became not only a matter of chemistry, but of orbital mechanics at its finest scale. The risk to spacecraft was indirect, but real. A nucleus stretched by tides might shed larger clumps, not dust alone but chunks measurable in meters. These would be few, scattered, unlikely to intersect any orbiter, yet their very possibility demanded attention. Even a single fragment, if untracked, could transform hazard into catastrophe. And dust, redirected by gradients, might sweep through broader arcs, intersecting trajectories where models had predicted emptiness. The lesson of tides is humility. Shoemaker, Levy 9, torn into pearls before Jupiter, remains the most famous demonstration, but countless smaller comets have fractured invisibly under lesser pulls. For an interstellar body like 3I divided by Atlas, whose interior was unknown and whose cohesion uncertain, tidal influences could tip a balance we did not know existed. The danger was not apocalypse, but unpredictability, the refusal of the comet to obey the neat lines of calculation. And yet, tides also promised revelation. If fragmentation occurred, the geometry of pieces could reveal internal weakness, density, porosity. If dust streams were widened, detectors could sample material from layers otherwise hidden. The sun's grip, though indifferent, could serve as experiment, exposing structure through stress. To watch an alien comet tested by gravity was to glimpse its biography, written not in orbits but in cracks. Philosophically, the image carried weight. Here was a traveler that had crossed interstellar darkness untouched, only to be pulled and tested by the modest tug of one yellow star. It was a reminder that fragility is universal. No matter how far a body has journeyed, no matter how ancient its path, the right force at the right moment can bend it, break it, scatter it into dust. And in that scattering, both danger and knowledge are born. Thus, tidal forces entered the narrative, not as a headline threat but as an undercurrent, a quiet, steady hand upon the comet's body. Invisible, inexorable, they shaped both hazard and opportunity. In the calculus of worst-case scenarios, they stood as a reminder that even the gentlest gradients can decide the fate of wanderers from the stars. By late summer of 2025, the flood of observations began to condense into clarity. Each new measurement, each point of light fixed against background stars, tightened the error bars on 3ATAI divided by Atlas's trajectory. The uncertainty ellipses that once sprawled across millions of kilometers shrank day by day. What had been speculation became prediction. What had been possibility became boundary. In the discipline of celestial mechanics, this shrinking of doubt is the heartbeat of progress. And yet, even as the orbit refined, vigilance did not relax. Scientists knew the danger of overconfidence. Outgassing, fragmentation, rotation-driven shifts all could still nudge the comet into deviations invisible until they manifested. The great paradox of prediction was this: the closer the comet came, the more data sharpened the models, but also the more volatile the comet became under the sun's heat. Certainty and uncertainty advanced together, locked in an uneasy embrace. The Minor Planet Center issued updated ephemerides almost daily. Each bulletin reassured, no collision course with Earth, no threat to planetary safety. For the public, that was enough. Headlines spoke of safe passage, of scientific curiosity without danger. But in the background, teams at NASA, ESA, and other agencies continued their quiet watch. For spacecraft near Mars, the margin for error was thinner. A dust stream shifted by only tens of thousands of kilometers, trivial on cosmic scales, could still intersect a satellite's orbit. Engineers spoke in the language of probability. The chance of significant hazard was low, perhaps vanishingly so. But low is not zero. In risk analysis, even a 1% chance of dust exposure was treated with rigor. The stakes were high. Billions of dollars in hardware, decades of mission planning, irreplaceable data flows. To safeguard them, even the slimmest risk justified vigilance. Astronomers, meanwhile, turned refinement into artistry. They accounted for every photon pressure, every whisper of non-gravitational force. They tested models against brightness variations, hunting for hidden accelerations. Each refinement was a kind of conversation with the comet, a dialogue in which data spoke faintly and models answered with curves. In that conversation, humanity sought not only prediction, but intimacy, to understand the stranger's behavior as more than numbers, to glimpse its personality. Still, anomalies persisted. Residuals in orbit fits hinted at forces not fully captured. Some nights, the comet glowed brighter than expected, as though minor outbursts had occurred. On others, its tail geometry shifted subtly, suggesting jets altering momentum. None of these deviations threatened Earth, but all of them reinforced the lesson. Interstellar visitors obey rules, but not always the rules we know. The mood became one of disciplined anticipation. The probability ellipses were now narrow, the broad strokes secure. Yet the worst-case scenarios remained alive in the margins. A sudden breakup, an unforeseen dust surge, an unmodeled plasma interaction. Scientists had no luxury of dismissal. To assume too much was to invite oversight. Vigilance itself was the shield. Philosophically, the refinement of orbit carried symbolism. The comet's path was ancient, written long before humanity emerged. Yet here we were, tracing it with precision, predicting its position to within kilometers, shrinking uncertainty with each night of measurement. Knowledge, fragile though it was, wrestled with the unknown and held its ground. But knowledge, too, carried humility, the acknowledgement that models, however fine, cannot eliminate chaos. Thus, as 3I divided by Atlas moved inward, humanity moved with it not in body, but in attention, in calculation, in imagination. The shrinking uncertainty did not erase mystery, it sharpened it. For the closer we came to knowing where the comet would be, the more vivid the question became. What, in its volatile heart, would it choose to do? By autumn of 2025, the campaign to watch 3ATI divided by Atlas had become a symphony of instruments. The great observatories of Earth, orbiting telescopes above the atmosphere, and robotic outposts around Mars all joined in a coordinated vigil. Each played its part, each gathered a fragment of the story, and together they wove a tapestry of observation unlike any mounted for a comet before. This was not only astronomy, it was planetary rehearsal, a collective act of vigilance in the face of the unknown. The James Webb Space Telescope turned its vast mirror toward the stranger, probing in infrared. There, in the wavelengths invisible to human eyes, the chemistry of the coma unfolded with exquisite detail. Molecules of carbon dioxide, carbon monoxide, and faint traces of water shimmered in its spectrum, confirming suspicions that this comet bore the fingerprints of a star system colder and more volatile than our own. JWST's sensitivity reached faint emissions that ground-based telescopes could only guess at, resolving ratios and isotopes that hinted at origins in distant, metal-poor regions of the galaxy. Hubble, though aging, remained invaluable. Its high-resolution imaging traced the coma's symmetry, watching for subtle jets, for asymmetries that might betray rotation or instability. Together with JWST, it provided a bridge between history and future, the Legacy Telescope and the new Sentinel, both bearing witness to the third interstellar visitor. Closer to Mars, orbiters prepared themselves not only as observers, but as participants. MAVEN, designed to study Mars's atmosphere, stood ready to detect cometary plasma and auroras. The Mars Reconnaissance Orbiter, with its sharp-eyed cameras, could capture dust halos if the geometry aligned. Even rovers on the surface, Curiosity, Perseverance might glimpse meteor streaks if grains entered the thin Martian sky. Each instrument was repurposed. adjusted, waiting for the possibility that Mars would serve as our proxy in the encounter. On Earth, the European Southern Observatory in Keck in Hawaii monitored brightness variations nightly, refining spin-state models. Radio telescopes joined, measuring dust flux through radar echoes. The global network resembled not curiosity, but vigilance, as if humanity had raised a net across the solar system, determined not to let this traveler slip past unseen. The collaboration extended beyond science. Space agencies shared predictions, synchronized models, compared strategies for spacecraft safety. Engineers rehearsed maneuvers, rotating orbiters to minimize exposure, timing safe mode entries, ensuring solar panels faced away from potential streams. It was a rehearsal for planetary defense, not in the sense of averting collision, but of managing exposure, of learning how to adapt to cosmic visitors that arrive without warning. In the data, tension built. Each new spectrum confirmed the comet's strangeness. Each new orbit solution confirmed its trajectory. Yet the unknown remained. How volatile would it become near perihelion? Would it hold together or fracture? Would its dust tail sweep broadly enough to touch Mars? Instruments did not answer questions, they sharpened them. Observation fed not certainty but preparation. Philosophically, the image was profound. For the first time in human history, an interstellar comet was studied not by a single instrument, not by a few telescopes scrambling, but by an orchestra spanning worlds. Earth, orbit, and Mars acted in concert. It was as though humanity itself had stretched its senses outward, evolving in real time into a solar system species. The comet was not only an object of study, it was a test of coordination, a mirror showing how far our reach had grown. Thus, Section 20 closed on a paradox. Vigilance both reassured and unsettled. We knew more than ever, yet what we knew was how much remained uncertain. But in that uncertainty, we found unity. The stranger from the stars drew us together, scientists, engineers, instruments, planets, into one sustained gaze at the dark. Precision became the obsession. As 3I divided by Atlas brightened on its inward approach, the cadence of measurements accelerated. Every night that skies cleared, observatories captured fresh astrometry. Tiny dots of light fixed against catalogued stars, each position refined to fractions of an arcsecond. The data streamed to the Minor Planet Center, then into the predictive engines at JPL. With each update, ephemerides sharpened, arcs smoothed, and the margins of error collapsed into narrower bands. The process was relentless, almost ritual. A new observation meant recalculation. Recalculation meant updated forecasts, and forecasts flowed instantly across the global network. Astronomers spoke in the language of covariance, ellipses, and sigma levels, but the underlying goal was simple: to know exactly where the comet would be and when. Such precision was not for spectacle but for safety. Instruments on Mars, orbiters in delicate trajectories, and rovers vulnerable only through their sky, all depended on ephemerides accurate enough to anticipate even diffuse encounters. Software pipelines ran continuously, blending astrometric data with models of non-gravitational accelerations. Each jet, each faint asymmetry in outgassing, was parameterized, tested, and folded into predictions. In some runs, the comet's dust tail cleared Mars entirely. In others, it grazed orbital altitudes. Engineers studied both outcomes, preparing contingency plans. Automated decision loops were rehearsed. If brightness surged, if dust densities exceeded thresholds, if ephemerides shifted by more than tolerances, spacecraft would pivot, shutters would close, detectors would sleep. The choreography resembled air traffic control, but on a cosmic scale. Spacecraft across 2 planets were synchronized with predictions refined nightly by telescopes half a solar system away. Each instrument became a node in a network, each update a line in a shared script. The comet itself was the conductor, and humanity listened for its tempo in the data. This automation of vigilance carried both comfort and unease. Comfort, because the process worked, uncertainty shrank, coordination grew, and the sense of readiness spread. Unease, because even perfect precision could not control the comet's behavior. A sudden outburst could render models obsolete within hours. A breakup could scatter fragments on trajectories no software could predict in time. Engineers knew the truth. Ephemerides guide, but they do not guarantee. Still, the act of refining ephemerides was an assertion of agency. In the face of a visitor from another star, humanity declared it would not be passive. We could not alter the comet's course, but we could anticipate, adapt, and defend our machines. Each decimal shaved from the uncertainty ellipse was a small victory against chaos. The philosophical resonance was clear. For millennia, comets were omens precisely because they defied prediction, appearing suddenly, wandering erratically, defying the clockwork of planets. Now, for the third interstellar comet, prediction itself was the story. What had once been the language of prophecy was now the language of covariance, matrices, and sigma confidence, yet the awe remained. Beneath the mathematics lay the same human impulse, to know what the sky will bring and to prepare for its arrival. Thus, Section 21 closed on an image of discipline. Humanity gathered not in fear but in vigilance, transforming uncertainty into manageable risk through calculation and coordination. The comet continued its glide, indifferent to our watch, but in its indifference, it forced us to sharpen our gaze, to measure with greater care, and to admit once more how fragile precision remains before the vastness of the unknown. Dust was no longer poetry alone, it became calculation. In control rooms on Earth, engineers translated the comet's projected activity into numbers that spoke directly to spacecraft survival. How many particles per cubic meter? What velocities? What cross-sections of fragile sensors and solar panels might those grains encounter? The problem was no longer abstract astronomy. It was exposure budgets, survival thresholds, and mitigation strategies. Models began with the nucleus size capped at about 1 kilometer and extrapolated dust production from gas release rates. If the comet shed 10 to the power of 25 molecules of carbon dioxide per second, how much dust mass might accompany it? What fraction would consist of submicron grains? What fraction of millimeter chunks? Equations filled with coefficients of drag and velocity distributions, feeding into Monte Carlo simulations. The goal was simple: predict how many grains might strike a square meter of spacecraft surface if Mars passed near the tail. The numbers varied, swinging with assumptions. Some models predicted only a handful of particles across an entire mission negligible, little more than cosmic background. Others suggested bursts of denser flux if the comet fragmented, perhaps hundreds of grains per square meter during peak passage. At tens of kilometers per second, even a grain the size of dust on a windowsill could gouge metal, pit mirrors, or scratch star tracker lenses. Engineers weighted probabilities, not certainties, aware that even the low-end scenarios demanded respect. Protective strategies were discussed. Spacecraft could rotate so that thickest shielding faced forward, minimizing exposed instruments. Solar panels could be tilted edge-on, sacrificing power efficiency for survival. Cameras could close shutters, spectrometers could sleep. These maneuvers required precise timing. Too early, and science would be lost. Too late, and protection would fail. Thus, the dust to cross-section calculations became the clockwork around which contingency plans revolved. Even the simplest designs, the layered walls of Whipple shielding, entered the conversation. A thin sacrificial sheet, placed centimeters ahead of critical surfaces, could shatter incoming grains, dispersing energy before impact. Some orbiters carried such defenses, others did not. The tally of shielding, mass, and orientation was reviewed mission by mission, each spacecraft assessed for resilience. And still, the models circled back to uncertainty. The chemistry of 3I divided by Atlas implied vigorous CO2 jets, capable of lofting particles faster and farther than expected. Breakup scenarios could increase dust production by orders of magnitude. Non-gravitational forces might alter tail geometry, sweeping denser streams into regions once thought safe. Every calculation carried caveats, and every caveat became a margin of caution. Yet scientists reminded one another, dust is danger, but it is also treasure. A few grains striking detectors could carry isotopic fingerprints of alien star systems. To measure their ratios of hydrogen, carbon, or oxygen would be to sample the chemistry of another sun's nursery. For MAVEN or TGO, a chance encounter with dust might become the most important measurement of their missions. The line between hazard and discovery blurred, as it so often does in space exploration. The philosophical undercurrent deepened. Dust, the smallest and most overlooked material in the cosmos, became the arbiter of risk. Not the comet's mass, not its orbit, but its microscopic grains dictated the scale of human preparation. It was a reminder that survival for spacecraft, for species, often depends not on deflecting giants, but on enduring specks. Thus, Section 22 stood on the threshold of calculation and caution. Cross-sections, flux rates, and shielding schemes became the vocabulary of vigilance. The comet itself continued, shedding its grains in silence, indifferent to the fact that human machines now measured, modeled, and braced against each one. Mars, with its thin veil of atmosphere, could not hope to shield itself from the whisper of alien gases. As 3I divided by Atlas drifted near perihelion, scientists considered not only dust and fragments, but also the interaction of volatile outflows with the Martian sky. A comet is more than a nucleus. It is an expanding cloud of chemistry. If Mars brushed the edge of that cloud, its atmosphere would become a stage for reactions never before witnessed. The primary constituent of the Martian sky is carbon dioxide, cold and tenuous. Into this would stream molecules from the comet's coma, water vapor, carbon monoxide, cyanides, traces of hydrocarbons. Ultraviolet sunlight would strike them, breaking them apart, igniting chains of photochemistry. For hours, perhaps days, Mars's exosphere could shimmer with alien ions, a cocktail of species never native to its world. MAVEN's instruments, designed to sniff such changes, might record shifts in electron density, sudden spikes in exotic emissions. Heating effects were also considered. The density of the coma, though diffuse, could in theory deposit energy into Mars's upper atmosphere. Models predicted only modest rises, fractions of a degree, localized and brief, but even subtle warming could alter circulation temporarily. To witness such heating would be to glimpse how atmospheres across the galaxy might respond to cometary infall, a natural experiment offered once in a generation. For rovers and landers, the effects would be invisible except as meteor trails. If fragments intersected Mars's air, streaks of light would arc across the thin sky, burning briefly before fading. Cameras could capture them, spectrographs could resolve their colors, each line revealing chemistry forged under another star. For scientists, even a handful of such meteors would be priceless, direct samples of interstellar dust interacting with a planetary atmosphere. And yet, the worst-case scenarios lingered. Could volatile rich plumes temporarily saturate Mars's ionosphere, disrupting communications between orbiters and Earth? Could charged particles induced by cometary plasma currents scramble electronics, even briefly? The probabilities were low, but the consequences were non-trivial. Engineers drafted contingencies, alternate relay paths, redundant communication windows, commands queued in advance in case of blackout. Philosophically, the encounter carried symbolism. Mars, long seen as a mirror of Earth's past, now stood ready to host a drama. Earth itself was spared. For the first time, another planet might be brushed by the breath of an interstellar visitor, while human machines looked on. It was as though the galaxy had chosen Mars as proxy, delivering to its thin sky the chemistry of another world. In the faintest interactions, a whiff of alien molecules, a meteor streak across ochre twilight humanity would glimpse connection. The solar system was no island. Its planets were participants in the broader traffic of galactic matter. 3I divided by Atlas would not collide, would not scar, but it might leave a trace in chemistry, in plasma, in light. And in that trace lay the possibility of learning not just about a comet, but about the nature of exchange between systems. Thus, Section 23 closed on anticipation. Would Mars's sky remain unchanged, indifferent to the comet's passage? Or would it, for a fleeting night, glow with alien fire, recording in its tenuous air the presence of a traveler from another star? The answer would be written not in myth but in telemetry, waiting to be read. For some, 3I divided by Atlas was not a threat at all, but an opportunity wrapped in ice and dust, a chance to rehearse the protocols of planetary defense. The comet's orbit posed no danger to Earth. It would pass safely, its hyperbolic path carrying it outward again into the galactic dark. And yet, the very fact of its arrival forced space agencies to act as though the stakes were higher. The visitor became a live fire exercise, a drill scripted not in conference rooms but in the sky itself. The logic was clear. True planetary defense is not only about intercepting incoming asteroids, it is also about vigilance, coordination, and communication. 3I divided by Atlas demanded all three. Observatories on Earth coordinated with those in orbit, feeding real-time astrometry to central hubs. Prediction models updated nightly, warnings cascaded across networks, and spacecraft operators rehearsed safe-mode contingencies. What would happen if dust flux spiked? If an outburst shifted the comet's tails? If Mars orbiters faced sudden exposure? Each question echoed scenarios engineers had sketched in tabletop simulations. Now, those scenarios were tethered to a real object. Comparisons to past events lent perspective. In 2013, when asteroid 2012 DA-14 skimmed close to Earth on the same day a smaller body exploded over Chelyabinsk, humanity was reminded of its vulnerability. In 2014, when comet-siding spring swept past Mars, the planetary science community learned the value of rapid coordination, moving orbiters to the far side of the planet during closest approach. 3I divided by Atlas combined both lessons, the need for constant monitoring and the need for agile response when predictions brush close to spacecraft pathways. International agencies treated the comet as a rehearsal. NASA, ESA, JAXA, ISRO, each contributed resources, each synchronized models. Amateur astronomers too played their role, feeding positional data that refined ephemerides in ways large observatories alone could not match. The entire infrastructure of planetary defense flexed its muscles, not to ward off collision, but to measure resilience. The public saw headlines about a comet from another star, safe and spectacular. Few glimpsed the quieter work beneath, the endless loops of simulation, the decision trees prepared in case Mars orbiters had to shield themselves, the long teleconferences stitching together time zones and disciplines. This was the hidden choreography of vigilance, the work of agencies preparing for a day when an object's trajectory might not pass so harmlessly. And beyond the mechanics, there was symbolism. To frame 3I divided by Atlas as rehearsal was to admit that humanity now lives in an age of planetary responsibility. Our gaze outward is not only for curiosity, but for defense. We can no longer afford to think of the sky as passive backdrop. Visitors arrive. Most, like this one, pass safely. But someday, one may not. By treating each arrival as practice, we sharpen readiness against that eventuality. The worst-case scenario here was never impact. It was complacency, the failure to learn from a gift of rehearsal. By avoiding that complacency, humanity gained more than data. It gained confidence and the beginnings of a planetary culture of vigilance. Thus, Section 24 found meaning not in catastrophe but in preparation. 3. I divided by Atlas became more than a comet. It became a mirror of our maturity as a species. In its harmless glide, it asked, "Are you ready for the one that will not be harmless?" And in the quiet rehearsals of 2025, humanity whispered back, "We are learning." No comet arrives without stirring the imagination of engineers who dream of pursuit. With 3I divided by Atlas, those dreams were tempered by time. Its discovery came too late to mount an intercept. And yet, as scientists studied its strange chemistry and fragile size, the conversation widened to a different horizon. What if next time we were ready? The idea of interstellar intercepts has lived on drawing boards for years. Concepts like NASA's Comet Interceptor mission, scheduled for the late 2022s, are designed to launch and wait in solar orbit, poised to sprint toward the next suitable target. For objects like Oumuamua, discovered too late and moving too fast, such missions remain dreams. But 3I, divided by Atlas, bright and gaseous, fit the ideal profile. If only a craft had been waiting, it could have flown through the coma, sampling dust, imaging the nucleus, tasting chemistry untouched since another star was born. Design studies multiplied. A fast-response spacecraft, launched from Earth within months, equipped with high delta-V propulsion, could in theory intercept a visitor like 3I divided by Atlas. Solar sails, nuclear electric drives, or modular propulsion stacks all were proposed as means to chase an interstellar comet. Even more ambitious were standby interceptors, spacecraft placed in long-duration parking orbits, dormant until a visitor was discovered. The discovery of 3 interstellar objects in less than a decade lent urgency. Such visitors were not flukes, but a pattern. Preparation was no longer speculative, it was necessary. The worst-case framing sharpened these ambitions. What if one day the interstellar visitor's path veered closer, brushing Earth instead of Mars? We would need not only telescopes to watch, but spacecraft to meet it, characterize it, and if necessary, plan deflection. Even if 3I divided by Atlas posed no direct danger, it became the stand-in for the hazardous stranger yet to come. Every discussion of intercept was also a discussion of defense. Philosophically, the dream of intercept carried resonance. For centuries, comets were omens, beyond reach, streaking across skies as mysteries. Now, humanity dared to imagine not only watching but touching, not only fearing but meeting. To fly beside an interstellar comet would be to clasp hands with another star system, to carry out the first handshake between suns. Such imagery belonged as much to poetry as to engineering, but it was no less powerful for it. And so, in conferences and white papers, 3I divided by Atlas became both example and warning. It reminded scientists that readiness must precede discovery. The galaxy will continue to cast fragments across our path. Some will pass harmlessly, some will bring hazards. To study them, to prepare for them, requires not improvisation but foresight. The comet itself was fleeting, a faint traveler slipping back into the dark. But the lessons it inspired, the need for intercept capability, for fast launch readiness, for global coordination would remain. Thus, Section 25 closed not on the comet itself, but on the future. 3. I divided by Atlas could not be chased, its chance had passed. But the next one, the fourth interstellar visitor, may not escape so easily. And in the quiet halls of space agencies, the plans took shape, seeded by the ghost of this encounter, the resolve that next time humanity would be waiting. No comet escapes the gravity of imagination. As 3I divided by Atlas brightened, speculation spilled beyond journals and into headlines, blogs, and late-night broadcasts. Some declared it an omen, echoing ancient fears. Others leapt to wilder conjectures. Could this be artificial? Was it a probe sent by another civilization? The fact that Oumuamua had once inspired such debates only fueled the cycle. Now, with a third interstellar object, the narrative reignited. Perhaps we were not only observing nature, but receiving a message. Scientists, careful and disciplined, pushed back. The spectra revealed gases consistent with natural ices. The coma and tails followed physical laws, not exotic designs. No radio signals emanated from its path. In every respect that could be measured, 3I divided by Atlas behaved like a comet, fragile, volatile, unpredictable, yes, but natural. Yet the absence of evidence did not quench the fire. The public imagination thrives on possibility, and interstellar visitors ignite the oldest questions. Are we alone, and would we recognize a messenger if one came? Social media magnified the drama. Photographs of faint smudges became viral, labeled with captions of doom or wonder. Amateur astronomers posted nightly updates, their grainy images treated like dispatches from a frontier. Rumors spread faster than facts, each claiming insight into the comet's intentions. To many, the nuance of orbital mechanics mattered less than the poetry of narrative. In their retelling, 3I divided by Atlas became a harbinger, a wanderer bearing secrets, a test of humanity's readiness. The danger in such speculation lay not in science, but in perception. Planetary defense requires trust. If agencies say safe, yet the public hears threat, anxiety spreads. If headlines promise apocalypse, vigilance may collapse into fear. The worst case is not only physical impact, but social fracture, the loss of confidence in scientific truth, the erosion of calm in the face of cosmic events. And yet, there is a paradox. Speculation also sustains curiosity. Without the allure of mystery, without the whisper of what if, the public might never look up. Ancient civilizations wove myths around comets precisely because they inspired both awe and dread. In the modern age, myths are replaced with theories of aliens, probes, hidden messages. They are unscientific, but they keep attention alive, ensuring that comets are not ignored. Philosophers noted the symmetry. A comet from another star awakens in us the same reflexes it stirred in our ancestors. Wonder and fear entwined. The difference lies in our tools. Where they told stories of gods and omens, we build telescopes and models. Yet the psychological need is unchanged. We want meaning from the stranger. We want to know not only what it is, but why it came, as if the galaxy itself must have intention. For scientists, the challenge was balance. To dismiss speculation outright risked alienating the public. To indulge it risked distorting truth. Instead, they chose the middle path. Affirm the wonder, acknowledge the mystery, but anchor it in data. 3I divided by Atlas was natural, they said, and that truth was no less extraordinary. For what greater story could there be than a shard of another star system drifting into ours, offering a sample of alien chemistry without malice or design? Thus, Section 26 turned inward, reflecting not on the comet itself, but on humanity's reaction to it. The hazard lay not only in dust or fragments, but in stories told too fast, in fears spread too far, in meanings projected onto silence. In the end, the comet remained mute, indifferent to our myths. It was we who filled its silence with voices, some of science, some of imagination, all of them revealing as much about us as about the stranger from the stars. The paradox deepens when science itself leans into imagination, for even as astronomers dismiss alien probe theories in press conferences, behind closed doors they allow themselves to ask the forbidden questions. What if, against probability, one of these visitors did carry a signature of intelligence? Would our instruments be sensitive enough to detect it? Would we recognize the difference between natural chaos and deliberate design? These quiet speculations do not appear in peer-reviewed journals, but they exist in whispers and thought experiments, a necessary exercise in humility. With 3I divided by Atlas, some scientists replayed the Oumuamua debate. Harvard astrophysicist R.V. Loeb had stirred controversy years before by suggesting Oumuamua could be artificial, an outlier whose anomalous acceleration hinted at technology. Though most disagreed, the discussion opened a space where such radical ideas could be entertained without immediate dismissal. Now, with Atlas's more ordinary cometary behavior, most dismissed the idea outright. But the precedent remained. Interstellar objects force us to confront the boundary between science and speculation, to test how far reason may stretch before myth takes over. This boundary is fragile, too rigid, and science risks blindness, dismissing the extraordinary before it can be measured. Too loose, and science risks collapse into fantasy. The dance between skepticism and wonder defines our progress. Galileo speculated about the mountains of the moon before anyone could prove them. Einstein imagined riding a beam of light before relativity was formalized. Speculation, when disciplined, is the engine of discovery. The danger is not in imagining, but in failing to tether imagination to evidence. 3I divided by Atlas was, in the end, a reminder of humility. It behaved like a comet, yes, but a comet from another star system, carrying with it material older than our Sunday. That fact alone stretches the imagination beyond comfort. When humans grind fragments in labs decades later, measuring isotopes unknown, perhaps then we will confront how much we do not yet understand. And perhaps, just perhaps, we will wonder whether the truly alien is not intelligence, but nature itself weaving chemistry and physics in ways we have never seen before. Meanwhile, the public clung to stories. Blogs speculated about hidden codes in the comet's trajectory, as if its orbit spelled out messages across constellations. Documentaries whispered about cosmic emissaries. Even novels and films took shape, inspired by the visitor that crossed our sky briefly before vanishing forever. The comet itself remained silent, but it seeded narratives across disciplines, across imaginations, across fears. The worst-case scenario here was subtle, not destruction, not impact, not collapse of satellites. It was a distortion of truth, a slow erosion where myth and fact blurred, where the boundary between science and story frayed. For civilizations depend on clarity. Without it, fear can be weaponized, and wonder can be misled. The lesson of 3I divided by Atlas was not only about comets, but about ourselves. How fragile truth becomes when speculation outruns patience. Yet speculation is also resilience. To imagine the worst is to prepare for it, to consider alien messengers, collapsing vacua, cosmic hazards. This is how humanity survives. In our fears lie our defenses. In our questions lie our discoveries. The comet, indifferent, passed through, but it left behind this paradox. We are both endangered and empowered by imagination. As the weeks turned into months, 3I divided by Atlas began to fade. Its outburst subsided, its coma thinned, and its once bright arc across the instruments dimmed into near invisibility. The frenzy of speculation quieted, the headlines dwindled, and what remained was the slow, methodical work of science. Yet in that fading lay a profound reflection. The comet's physical retreat mirrored the ebbing of human attention, as if its existence had been measured not only in photons, but in our capacity for wonder. But for researchers, the story was far from over. The data gathered in those frantic months would feed models for decades. Every spectrum preserved, every orbital parameter refined, every brightness curve archived, all of it would become fuel for future generations. 3I divided by Atlas, though gone from sight, was not gone from knowledge. In this way, comets become paradoxical, ephemeral in presence, eternal in memory. What did the scientists see in its departure? For some, relief. The worst-case scenarios had not materialized. No catastrophic fragmentation, no surprise trajectory shift, no unexplained emissions. For others, disappointment. Without anomaly, the comet was ordinary, a reminder that not every visitor from interstellar space carries revelation. But for the most reflective minds, the lesson was different still. The very ordinariness of 3I divided by Atlas was its gift. It taught that even a shard of frozen dust, unremarkable by cosmic standards, could journey across light years to brush against our awareness, and that this simple fact was enough to unsettle and expand us. Humanity, in turn, reflected on its own fragility. The worst-case scenario had always been more about us than about the comet. What if we failed to prepare? What if we miscommunicated? What if panic replaced reason? The comet left, but those questions remained. And as policymakers revisited planetary defense strategies, as educators debated how to communicate cosmic risk, 3I divided by Atlas became a case study not in disaster, but in preparedness. Its fading also echoed deeper truths. All things pass: comets, civilizations, even stars. Yet the meaning of their passing depends on the stories we tell. Ancient skywatchers feared comets as heralds of doom. Modern astronomers read them as messages from the past. Neither view is wrong. Each reflects humanity's search for orientation in a universe indifferent to our fears. In the last frames captured by telescopes, 3I divided by Atlas appeared as a smudge, barely distinguishable from background noise. A visitor reduced to almost nothing, and yet, within that blur was the history of another star system, preserved across millions of years, delivered briefly into our care. In its fading light lay the echo of a truth that is both terrifying and beautiful. The universe does not need us to notice, but we are changed forever when we do. Long after 3I divided by Atlas vanished into the outer dark, its ghost lingered in human thought. Conferences revisited its arc, workshops passed its data, and graduate students built careers on models born from its brief appearance. But beyond academia, its imprint seeped into culture. Paintings reimagined it as a burning messenger. Poets gave it voice as a solitary traveler. Musicians composed symphonies inspired by its silent glide. The comet, mute and indifferent, became a mirror for human creativity, proof that science and art share a common root in wonder. For philosophers, the lesson reached deeper. They asked, what is the meaning of worst case when applied to the cosmos? Is it destruction, the obliteration of our fragile species by a careless fragment of rock and ice? Or is it silence, the realization that the universe offers us encounters without explanation, leaving us perpetually uncertain? To some, the worst case was extinction. To others, it was insignificance. 3I divided by Atlas, in its quiet passage, embodied both. Theologians, too, found resonance. Some cast the comet as a reminder of humility, a symbol of creation beyond human control. Others saw it as a test. Could humanity confront cosmic mystery without surrendering to fear? Ancient traditions often tied comets to divine will. In a secular age, the divine is replaced with equations, but the awe remains. Even stripped of myth, the sight of an interstellar visitor forces us to kneel inwardly before the vastness of what we do not know. In the realm of policy, Atlas became a footnote in planetary defense handbooks. Reports concluded, "No threat detected, future vigilance required." Yet buried within the technical language was a sobering truth. Our species remains unprepared for the improbable. The visitor caused no harm, yet it reminded us how easily we could be caught unaware. The worst case is not that a comet will strike, but that one day it might, and that we will not be ready. In literature and discourse, Atlas came to symbolize the fleeting nature of cosmic encounters. Unlike Oumuamua or Borisov, it did not shock with anomaly nor blaze with brilliance. Instead, it faded quietly, leaving behind questions rather than answers, and perhaps that was its greatest power. It reminded humanity that not all mysteries explode with revelation. Some dissolve into silence, forcing us to reflect on the fragility of knowledge itself. The comet's departure echoed the rhythm of mortality. Lives, too, flare briefly and vanish, leaving traces in memories, in art, in history. To contemplate 3I divided by Atlas is to confront our own impermanence, to accept that we, like comets, are wanderers through a cosmos that neither welcomes nor resists us. The worst case, then, may not be annihilation, but forgetting to pass through existence unnoticed, unremembered. Thus 3I divided by Atlas, though gone, remained alive in the human mind, a shard of interstellar ice transformed into a meditation on destiny. Its story was never about impact alone, but about reflection, a reminder that the universe's most dangerous gift is not chaos, but meaning. The last echoes of 3I divided by Atlas became whispers in datasets, footnotes in reports, fragments in archives. Astronomers turned their lenses elsewhere, scanning skies for the next visitor, yet in quiet moments their thoughts returned to that fleeting guest. The comet had come and gone, and in its wake it left not destruction but perspective. The worst case had not unfolded, no shattering fragments, no invisible poisons, no sudden plunge toward Earth. And yet the true danger was never physical alone. It was existential, the recognition of how small we are, how vulnerable, and how unprepared for the infinite possibilities drifting through the cosmos. The object now recedes toward the abyss, its dust tails thinning, its nucleus darkened. It becomes again what it always was, a fragment of another sun, indifferent to the drama it sparked among mortals. Humanity, left behind, continues to wonder, was it a warning, a rehearsal, a lesson, or simply a passing shadow, no more significant than countless others that cross the galaxy unseen? And so we return to the central question: what is the true worst-case scenario? Is it annihilation by cosmic chance, or paralysis by cosmic awe? Is it the silence of the universe, or the stories we invent to fill that silence? The answer lies not in the comet itself, but in us, in the way we respond, in the vigilance we maintain, in the humility we accept before forces greater than ourselves. In the final tally, 3I, divided by Atlas, harmed nothing, yet it changed everything. It reminded us that interstellar space is not empty, that strangers may appear without warning, that our place in the universe is both fragile and profound. Its legacy is not fear, but reflection, a call to prepare, to wonder, and to endure. And now, as the narrative slows, let the comet drift away in your mind's eye. Imagine the dark canvas of space, unbroken, save for a single faint trail dissolving into nothing. The panic has ebbed, the questions softened. What remains is a calm awareness that the universe moves on, vast and eternal, while we are but listeners for a brief span of time. The stars return to their quiet brilliance, no longer eclipsed by fear or speculation. Telescopes turn, notebooks close, and the night sky resumes its steady rhythm. In that rhythm lies comfort, a reassurance that even as visitors pass, the cosmos continues, indifferent yet steady. The worst cases imagined fade like dreams upon waking, replaced by the gentle truth that life, for now, endures. Let your thoughts soften with the fading light. See the comet no longer as a threat but as a reminder of the resilience of Earth, of the curiosity of humankind, of the beauty hidden in passing encounters. Each shard of dust that escapes into the void is a fragment of story, carried beyond reach, yet never beyond imagination. As you breathe slowly, feel the vastness settle not as fear but as peace. The universe is immense, yes, but it has granted us this moment of reflection. The comet is gone, the danger unrealized, and in its absence remains a quiet gift, perspective. So let the comet go, let it vanish into the silence that birthed it. The sky above remains, the earth beneath holds steady, and within you a calm knowledge glows. We are fragile, but we are here. We are temporary, but we are aware. And for tonight, that is enough. Sweet dreams.